So we're going to look at the chemical kinetics quiz. And this comes from the Kaplan suite of problems for the PCAT. And for question number 2, we are given a sample reaction where SO3 reacts with H2O to produce H2SO4. And we're to use this information to derive an explicit rate law. So let's talk about how we do this. So I want to be able to look at the data and then at the same time to show you how I interpret the data. So we have a number of experiments, and we want to choose 2 experiments where the concentration of one of the reactants doesn't change while the concentration of the other reactant does change. So if we look at experiments 1 and 2, notice that the concentration of H2O is constant while the concentration of SO3 doubles. And so we know that V equals the rate constant K times the concentration of SO3 to some power X times the concentration of H2O to some power Y. Now, the rate constant is a constant proportionality. We're just going to conveniently forget about the rate constant for a moment. And H2O's concentration doesn't change. And 1 to any power is equal to 1. That effectively removes K and removes H2O to the Y from our analysis between experiments 1 and 2. The rate quadruples. Take the larger number, divide it by the smaller number. You have 0.052 divided by 0.013. That's the same as 52 divided by 13, which is exactly 4. So the rate changes by a factor of 4. SO2 changes by a factor of 2. So this analysis simplifies to 4 equals 2 to the x. X definitely must be equal to 2. So 2 is a possibility for SO3 in A, but not in B, and not in C, and not in D, so we're done. The best answer is A. Yeah. All right, so let's look at number 2. Okay, so question number 3, we have the same data table, and it's important to remember we have the same reaction, and our previous answer gave us our kinetic rate law. So let's rewrite our answer from A. V equals K concentration of SO3 to the second power concentration of HO2. Now, what is inferred here is that the exponent is a 1. And we have a data table where we have X. And we need to figure out what does X need to be in order to be consistent with all of the data. And so there's a couple ways of tackling this problem. For example, I know that K is unknown. We could calculate K, but let's see if we can do it without having to calculate K. So I know that K has to have the same value, which is going to be V divided by concentration of SO3 to the second power, concentration of H2O to the first power. No matter what experiment I use. So let's use experiment number 1, where V is 0.013 and SO3 is 0.1 squared and H2O is 0.01. That has to have the same value of K that we would have in trial 3, which is where I have my X variable. That's equal to 0.234 divided by X squared divided by 0.02. Now this isn't optimal because I have an X squared and I have numbers that are decimals, but this is a solvable problem. So let's look at how we can do this carefully. I would put everything in scientific notation. I think that makes it a little bit easier. So how about 1.3 times 10 to the minus 2 times 2 times 10 to the minus 2 times X squared. All I'm really doing is cross multiplying. And so this gives me 2.6 times 10 to the minus 4 X squared. And this is equal to, now let's go to this side. We have 2.34 times 10 to the minus 1 times, this will be 1 times 10 to the minus 1 squared. That's the same as 1 times 10 to the minus 2. And then again I have 1 times 10 to the minus 2. So simplifying this just a bit, we have 2.6 times 10 to the minus 4 X squared equals 2.34 times 10 to the minus 6. I can divide both sides and then take the square root. Now 2.34 divided by 2.6 is going to be about 0.9 times 10 to the minus 2. So when I take the square root of this, what would be useful is to put it in notation that I can easily use. Of course, this is going to be X squared. So why don't we say X equals, and we could go 90 times 10 to the minus 4. And then when I take the square root of this, the square root of 90 is going to be about 9, and this is going to be about 10 to the minus 2. So I know that the decimal is going to, it can't be D because D is way too small. It can't be A because A is much too large. It's most consistent with B. Now that's one way of doing it. Okay, so for question 4, all of the following is false concerning reaction orders except. So we're looking for the statement that's true. The rate order of a zero order reaction is dependent on the concentration of the reactants. That's false for the following reason. Let's imagine that I have a reaction order that is 0th order with respect to reactant A. This actually simplifies to the rate is equal only to the rate constant, not to the concentration of A. So we can eliminate A. First order rate reactions have a rate proportional to the concentration of one reactant. That is always absolutely true. In fact, if we consider SN1 reactions, we've seen this before, that if I have T-butylbromide and I react it with H2O to produce T-butyl alcohol, this is dependent only on the concentration of the substrate, one reactant. So choice B is the credited response. Let's just look at C and D for a moment. If doubling the concentration of the reactant doubles the concentration of the reaction at second order, that's not true. If it was second order, we could write a reaction as V equals K, concentration of A squared. If I increase the concentration of A by a factor of 2, 2 squared is 4. The rate would quadruple, not double. After 4 half-lives, a radioactive sample will have 1/8 of its original concentration. Let's show why that's false. So I have 100%. After 1 half-life, I will have 50%, which is going to be 1/2. After 2 half-lives, I'll have 25%, or 1/4. After a third half-life, I'll have 12.5%, or 1/8. And after a fourth half-life, I will have 6.25%, or 1/16. So I would have 1/16, not 1/8, so that's also false. Best answer is going to be B. Number 5, which of the following is most likely to increase the rate of a reaction? So let's be real clear on these points because they're pretty simple to master and they're awfully important. First of all, unlike with equilibrium, increasing a temperature always has the effect of increasing the reaction rate. The reason for this is you speed up the molecules by giving them more kinetic energy. More kinetic energy equals more collisions. Imagine, for example, if you're driving on Interstate 240 at 60 miles an hour, and then on a second trip on 240, you travel 160 miles an hour. You are going to have a collision much more likely at 160 miles an hour than at 60 miles an hour. If I increase the temperature, I always increase the rate. So A is false. Decreasing the temperature would slow the reaction down. If I increase the volume of the reaction vessel, then molecular collisions may be more likely. They may not be more likely. That won't necessarily increase a reaction rate. If I have 100 people and I put them inside the Taj Mahal and I have them randomly rotate, vibrate, translate, there won't be nearly as many collisions as if I put them into my office and have them rotate, vibrate, and translate. Reducing the activation energy, choice C, will always result in a faster rate because you're going up a smaller energy hill. Fat boys say, I'd rather go up a small hill than a large hill, and I'll do it more quickly. If we look at D, decreasing the concentration of the reactant in the reaction vessel, that's like going on 240 where traffic is very light. You're not very likely to get into a collision. So all this is covered under collision theory. Choice C is the best answer that we are given, so C is the one that we want to choose. Number 6, all the following are true statements concerning catalysts except. The first definition of a catalyst that you obtain in biology is that a catalyst speeds up a reaction without being consumed in the reaction. So overall, it is not used up in the reaction. Now, in terms of a mechanism, it will be initially used up, but later it will be reproduced. Okay. You cannot use up a catalyst in a reaction. So a homogeneous catalyst just means it's in the same phase of matter. So if the reactants are liquid, it's a liquid. If the reactants are solid, it's a solid. If the reactants are gas, it's a gas. We know that it will lower the energy of activation. We know that it will speed up the slow step, but it will not be used up in the stoichiometry. Let's just go over these last three. These were choices that were correct. At equilibrium, the forward reaction continues. The change in reaction conditions can shift the equilibrium, and also the reverse reaction would continue. So C is not true, but A and B do occur. So that's a good answer choice. How will the equilibrium of the following reaction be affected if pressure is increased? Always ask 3 questions. What did I do? I only wish shadow would be a little bit more reflective like this. How can I reverse it? Really wish he would ask this question when he poops on the carpet. And 3, what is the chemical mechanism for which I do number 2? So let me illustrate this. What did we do? We increased pressure. How can I reverse it? I decrease pressure. In a chemical reaction, I can decrease pressure if I shift the reaction to where there are fewer moles of gas. I have 1 mole of gas in reactants, 2 moles of gas in products. I shift it to the left if the pressure is increased. So there's only 1 mole of gas in reactants. There's 2 moles of gas in products. I've increased the pressure, so in response to that, I want to decrease the pressure. How do I do that? I favor the side that has the least number of moles of gas. And the last question, following reaction which releases 30 kJ of heat, how will equilibrium be affected if temperatures decrease? Great question to ask. This is one I could definitely see occurring on an exam. So let's look at this equation through a different lens. We have H2, gas, plus Br2, gas, yields 2 moles of HBr gas. And I am told that the temperature is released. So heat is a product. If I decrease the temperature, I decrease the concentration of heat. That's what I did. How do I fix that? I want to increase heat. Well, how do I do that? I favor the side where heat is present. So in this case, I will shift to the right. I'll produce more HBr. So in an exothermic reaction, cooling the reaction helps us get more, but it slows the reaction down. In an endothermic reaction, increasing the temperature helps us get more and it speeds it up.